This video talks about improper integrals. So far we've talked about two different kinds of integrals. We have indefinite integrals that don't have bounds on them, and then we have definite integrals that do have bounds. It's the area under the curve from a to b. Usually up until this point a and b have been numbers, so we've had finite definite integrals, and now we're going to have infinite integrals, or what we call improper integrals, where either a or b or both of them are infinity or negative infinity. So here's an example of an improper integral. This one goes from 1 to infinity of 1 over x squared dx. So if we ignore the limits, we know how to find the integral of 1 over x squared. But the problem is we can't have infinity be one of our bounds because infinity is not a number. So we can't actually have something equal infinity. It can just approach infinity, which means we need to rewrite our integral where it's going from 1 to some number b, where b is approaching infinity. So we can't, that keeps us from having to plug in infinity. We're just now approaching infinity. And anytime we approach infinity or approach any number, we have to write it as a limit. So for all of our improper integrals, anytime you see infinity, you just need to bring it out and make it a limit. You can use whatever letter you want here. Typically I use A for the lower one and B for the upper one, but you can use whatever letter you want. Alright, so we write our limit out here going to infinity of 1 to b, and then the integrand stays the same, 1 over x squared dx. So basically we just ignore the limit part for a second, and we find the integral of 1 over x squared, which is negative x to the negative 1, and then we're going from 1 to b. So this part looks exactly the same as whenever we normally take integrals. The only thing we've added is this limit. Alright, so after we have the integrand, or we figured out we're going negative x to the negative first from 1 to b, we just plug in 1 and b. So I plugged in b, I plugged in 1, and then I rewrote it to make it look a little bit nicer, so b to the negative 1 is 1 over b, and then the negative comes. And then here we have a double negative, so that makes it a positive, and then this is 1 over 1, which is the same thing as 1. So this is the cleaned up version of that. Alright, so now we have the limit as b approaches infinity of negative 1 over b plus 1. When I plug in, well, I'm not really plugging in infinity, but you think back on how limits work, so I'm sort of plugging it in. As b gets really gigantic, I have 1 over a gigantic number, which means that this is going to go towards 0, and so this term doesn't really matter anymore. So really we just have 0 plus 1, or that equals to 1. And so because our integral is equal to 1, which is 1 is a finite number, meaning it's not infinity, that means our integral converges, because remember this entire unit is about whether things converge or diverge. Alright, so what it means for an integral to converge is that it's got a finite area, and this is really a biconditional, so if it has a finite area, then it converges. If it converges, it has a finite area. It goes either way. One of those implies the other. So this is a picture of an integral that converges. We're going from 1 to infinity with the curve 1 over x squared. So this area under here is finite, and it's equal to 1. It might seem like it's an infinite because we keep going on and on to infinity, but it really isn't, and you can prove that by taking the integral if you would like. Or you can trust me that this area under here is equal to 1, so this is an integral that converges, so it's got a finite area. If an integral doesn't converge, then the area is infinite, or vice versa. If it's an infinite area, then it doesn't converge. And we can take y equals x, right here, and the area under y equals x from 0 to infinity is going to be infinite, which means that this integral diverges because the area is not finite. It's an infinite area. Alright, here's another example. So we could have a negative infinity going to some number, and in this case, because it's on the bottom, like I said, I just usually make that a. So we're changing negative infinity to a, and then we have to write as a approaches negative infinity, which means we need a limit. So limit as a approaches negative infinity of the integral from a to 0 of x times e to the x dx. This one's a little bit long to do because we also have to do integration by parts to figure out what the integral is, but basically I'm just ignoring everything right now aside from the integral of x e to the x dx. So remember your rules for choosing u and dv. First I pick u so that it disappears, which means the x is going to disappear when I take the derivative, and then whatever's left over is dv. So dv is going to be my e to the x dx. And then I integrate to find that v is ex, and I differentiate to find that du is dx, and then I do u times v minus v du, and then the integral goes from a to 0, where my limit as a approaches negative infinity is still on the front of that. And then I can take the integral of this part, and I know the integral of e to the x is just e to the x. So x e to the x stays, and then minus e to the x, because that's the integral of that. And then I'm going from a to 0 as a approaches infinity. So there's a lot of pieces to this, because there's the thing that I got when I took the integral, those are the bounds, and then this is taking care of my infinity, because I can't have, well, I don't want to just leave a as a letter. I want to make sure that we get that negative infinity in there. Alright, so basically I'm going to leave the limit for the very last thing to do. I'm going to plug in a and 0 now. So 0 times e to the 0, this is just 0. And then minus e to the 0 minus, and then when I plug in a, I get a e to the a minus e to the a right here. So the first part's easy to clean up because that's 0 minus 1, which just gives me a negative 1. And then minus a e to the a right here. And then plus e to the a. And now I have to take the limit as I approach negative infinity. So the negative 1 part is really easy because there's nowhere, I don't have to plug in anything. Negative 1 is always negative 1 no matter how far to infinity I go. So that stays negative 1. E to the a, as I go from, as a goes towards a negative infinity, this is going to get smaller and smaller and get closer and closer to 0. So e to the negative infinity is 0. And then that just leaves my middle term here. And this is a part where I need to use L'Hopital's. So if you remember back on, or it might be a good time to review your L'Hopital's notes. But I have infinity times 0, which is kind of a problem, so I can do L'Hopital's on this, but first I need to write it as a fraction. So e to the a comes down to make e to the negative a, and now I have infinity over infinity, so I can do L'Hopital's, which means just take the derivative of the top, which is 1, and take the derivative of the bottom, which is negative e to the negative a. And now when I try to plug in negative infinity, I get 1 on the top, and then I get a positive infinity down here, so it's e to the positive infinity, which gives me 1 over infinity. And then 1 over infinity I know is just equal to 0. So the limit of this middle part is equal to 0. And so that is where this 0 comes from. And then I just add those three things together, which gives me negative 1. So this integral is equal to negative 1, which means that it converges. Alright, here's another example. For this integral, we're going from negative infinity to positive infinity, so we're going to need to change both limits on the integral. So our lower bound, we'll change it to a, the upper bound will change to b, so I'm going from a to b, and a is approaching negative infinity and b is approaching infinity. You can put those in the other order if you want to, it doesn't matter as long as you've got both of them. And then our integrand is 3y squared, dy. So we take the integral first, which is y cubed, and then it's going from a to b as a approaches negative infinity and b approaches positive infinity. You need both limits, but you can sort of evaluate these separately almost, because this one only depends on b and this one only depends on a. So if we think about, if we plug infinity in for b, that gives us infinity cubed, which is really the same thing as infinity. And then negative infinity, same thing, we have negative infinity cubed, which is still negative infinity, and then we have a minus sign here, so infinity minus negative infinity, which gives us a really infinity plus infinity, which is just infinity. So our integral from negative infinity to infinity of 3y squared dy is infinity, which means that our integral is infinite, and so it diverges. Here's an example for you to try. So if you're taking the integral from negative infinity to 0 of 2 to the x dx, pause the video here, and when you're ready to continue, we'll look at the solution. Alright, so here's our solution for this. We only have one infinity, so like the 0 can stay 0, and then we'll change our infinity to a or b or a smiley face or whatever you want to make this variable. Alright, so I made mine a, and a is approaching negative infinity because that's my lower bound of the integral of 2 to the x dx. And the integral of that is 1 over natural log of 2 times 2 to the x. This is just one that you have to memorize. And the limit as a approaches negative infinity of that from a to 0. So I start by plugging in 0 and a. Because 1 over natural log of 2 is a constant, you can sort of factor it out and have it at the beginning, or you can have it with each term, whichever one you would like to have. So I plug in 0 here, and I plug in a there. 2 to the 0 I know is just 1, and when I plug in 2 to the a is going to negative infinity, so really I have 2 to the negative infinity, which is just 0. And so 2 to the a becomes 0 when I take the limit as a approaches negative infinity. And my 1 over natural log of 2 follows me down here. 1 minus 0 is just 1, so I have 1 over natural log of 2 times 1, or just 1 over natural log of 2. That means that my integral is equal to 1 over the natural log of 2, which is just a number, so the integral converges. And that's it for this video. We'll be using improper integrals a lot for the rest of the unit, but not necessarily by themselves. They're going to be used for something else. Anyway, ask if you have questions.